Hello students, welcome to another session of All Fours e-learning program. In this session, we will talk about the electric field due to a charged spherical shell. So today's topic is electric field due to a charged spherical shell. Hollow sphere, electric field due to a charged hollow sphere. Then what is the formula for it? We will derive the formula and we will take up the various cases regarding this, right? So before going to this, let's have the review of what the necessary things that are useful to derive this, okay? Now I was telling you charge, a fundamental property. Every charge body produces a field around it. The space around the charge where you can feel its presence is electric field. Every charge body produces lines of force. So the lines of force are spread to a certain boundary, right? To an appreciable value, and that limited region, that is electric field. Every field has strength. Electric field intensity. The strength of the field is measured by electric field intensity. You know electric field intensity, it is force per unit charge. E is equal to F by Q. Later we have derived the formula for the electric field due to point charge. Then due to multiple charges by applying the principle of superposition, we have taken dipole electric field. Then flux. So electric flux is the measure of number of lines of force passing through a particular space. Count. The number of lines of force passing through a particular space, the measure of that count, the count of that number is called as electric flux. Flux density, electric field intensity or electric flux density both mean the same. So E is equal to phi by A. So cross multiplying, I get flux as E dot A. So the first useful formula here, what we need, so flux phi is equal to E dot A it is. Well, EA cos theta, flux is actually, so from this we get a phi is equal to EA cos theta. This is in uniform electric field. If it is non-uniform electric field, small flux, consider a small area element. In that small area element ds, let the electric field at all the points is almost same. Then the small flux is E dot ds. So therefore total flux, it is integral d phi, it is integral of E dot ds. So this is the basic formula we use. By definition of the flux, electric flux, total electric flux is the surface integral. It is the surface integral of the total flux from the enclosed surface. So it is a surface integral of E dot ds. Next, Gauss Law. You know the total flux through a Gaussian surface, enclosed Gaussian surface, the total flux through an enclosed Gaussian surface, it is directly proportional to charge enclosed inside the Gaussian surface, or it is 1 by epsilon naught times the charge that is enclosed inside the Gaussian surface. So equating these both, putting these two things together, the surface integral of the electric field intensity over the entire Gaussian surface, this is equal to charge enclosed inside by epsilon naught, right? So the surface integral of E dot ds is q inside. This is the mathematical form of Gauss law, which we will be using here to derive the expression for the electric field due to a charged spherical shell, right? So let's consider. So these are the things that are required for the derivation. Flux, it is E dot A, measure of the number of lines of force. E is electric flux density or electric field intensity, right? Flux is E dot A, EA cos theta. For uniform field, you can simply write it as EA cos theta because E is same at all the points in the field, so constant, simply EA cos theta. But in non-uniform electric field, where the field is varying from point to point, at different points the value of electric field is different. So consider a small area element, over that the small flux is E dot ds. Then the total flux, integrating the total flux, the surface integral of the total flux is E dot ds. Now that will be total flux. Equating that to Gauss law, we know according to Gauss law the total flux to a Gaussian surface is the charge enclosed inside times 1 by epsilon naught. So equating both, we will get this. So using this, we will be deriving the expression for a spherical shell. Now consider a hollow sphere, a spherical shell, a hollow sphere or a spherical shell, non-conducting or conducting, it does not matter, it is hollow, right? Let it be uniformly charged. Let the shell be uniformly charged with a charge capital Q. Let the charge that is given to the spherical shell be capital Q. And you know, if it is a conducting shell, all the charge will be existing only on the surface of the conducting, over the outer surface of the conducting shell, right? So all the charge is on the outer surface of the conducting shell like this. So charge is uniformly distributed. Let the center of the sphere be O and the radius of the sphere is capital R. Radius of the sphere is capital R. Now suppose radius of the sphere is capital R. Now if we are asked to find out the electric field, right, at various different points, we have to find out the electric field at the outside point of the sphere, or he may ask you to find the electric field intensity on the surface point of the sphere or the inside point of the sphere. So we will take up all the three cases separately. Now first we will consider the point outside the sphere. Let there be a point P outside the sphere at a distance small r. Right? So now we have to find out the electric field at this point P outside the sphere. It is at a distance smaller from the center of the sphere. Right? Mind you, you should always take the distance from the symmetrical center. If whatever charge distribution that is given, the distance should be measured from the center of the thing. Even while deriving the hollow cylindrical this thing, we have taken the distance from the center axis. Right? So therefore, from the center of the thing, the distance is smaller. So at this point P, we have to find out the electric field. Now, how to find the electric field? I was telling you while explaining about Gauss Law, when you use Gauss Law to measure the electric field, there are some steps to be followed. You have to follow certain steps. Right? The first thing is, imagine a Gaussian surface. So I was telling you, you have to cleverly imagine a Gaussian surface such that the shape of the Gaussian surface should be symmetric to the shape of the charge that is being given. It should be symmetrical, right? So since the charge that is given to us is a sphere, so you have to imagine a spherical Gaussian surface enclosing the sphere like this. So imagine a spherical Gaussian surface, right, enclosing the charged sphere inside it. First point, imagine a Gaussian surface. It should be symmetrical to the shape of the charge distribution that is given. Second, it should pass through the point where the electric field is to be determined. So I have to find the electric field at point P. So imagine a Gaussian surface such that it is passing through the point P. Right? So the Gaussian surface should pass through it. And now the Gaussian surface, we have imagined the Gaussian surface such that the center of the Gaussian surface and the center of the sphere coincide. The Gaussian surface is concentric to the spherical shell, concentric. Both the centers coincide. So for symmetrical charge distribution, the Gaussian surface is also symmetrical like this. Because for such region, what happens is the electric field, now from the center, the Gaussian surface is equidistant from the center. So all the points are at same distance. So the electric field at all the points will remain the same. The electric field at all the points on the Gaussian surface will have same magnitude. The magnitude will remain same. So that is the major thing for which you have to, while imagining the Gaussian surface, you have to take some important keen this thing. So you should cleverly imagine the thing so that the electric field will remain the same at all the points on the Gaussian surface. Right? So I have taken the spherical Gaussian surface which is equidistant from the center. So at all the points, the magnitude of the electric field will be same. Now how about the direction? Now we know this hollow sphere, the electric lines of force from the hollow sphere start from the surface and they are along the outward normal at any point on the surface. They are along the outward normal at any point on the surface there. So the direction of electric lines of force. So this hollow sphere, right, for this hollow sphere the electric lines of force exist such that the lines of force are along the outward normal. So the lines of force along the outward normal, so the electric field direction will be along these lines of force. We know that tangent drawn to the line of force gives the direction of the electric field intensity. So therefore the electric field intensity will be along the outward normal to the spherical charge sphere. So this is the electric field direction. Let the electric field at point P be some capital E bar. And the direction of the electric field is outward normal. If it is positive charge, the lines of force are outward normals, moving away from the surface to infinity. If it is negative charge, the lines of force would be along the same normal but towards the center of the sphere there. They will be along the same outward normal but the lines of force will be towards the center, but they stop at the surface. From infinity to the surface of the conductor. So the lines of force will just stop here, right? They will be along the normal only, but they just stop at the surface. Is it? For positive charge, outward normal. For negative charge, they are inward normals. The line of force will be along towards the spherical surface, inward and along the normals, right? So now let the magnitude of the electric field here be something like E, and the direction is outward normal. So the vector is E bar. First step, right? Later, let us consider a small area element ds on the Gaussian surface. So we are going according to the steps there, so that the method becomes simply very easy to evaluate the expression for the electric field. So consider a small area element on the surface of the Gaussian surface. A small area element ds. We know, I was telling you, whenever you consider a surface area, the direction of the surface area will be outward normal. If this is a surface, the direction is outward normal away from it. So for this surface, for this small area element, the direction is along the outward normal. So at this point, both electric field and the surface area element, both area element and the electric field both have same direction. They are parallel. So the angle between them is 0, right? So angle at any point, wherever you imagine, suppose if I imagine an area element here, that electric lines of force are along the outward normal, electric field will be this way, and the area element also has the direction outward, away from the surface along the outward normal. So at any point on the Gaussian surface, the electric field and the surface area element, area vector, both are parallel. So that is the beauty of this imagining the Gaussian surface. So I was telling you, while imagining the Gaussian surface, you should cleverly imagine it such that the electric field intensity in the surface are normal along the same direction. Electric field will be same at all the points on the Gaussian surface. So the surface should be symmetrical to the charge. So these are the points to be remembered, using which you have to imagine the Gaussian surface. So I have imagined a spherical Gaussian surface concentric to the charged sphere, equidistant like this, concentric to the charged sphere, so that at all the points the electric field intensity has same magnitude, and at any point the direction of the electric field and the area element is same. Now, let the small flux coming out of this area element be some d phi. Small flux coming out of this area element be d phi. So therefore, the small flux d phi. So d phi is equal to, we know small flux d phi is E dot ds. So it is E dot ds bar. But the electric field and this area element both are in same direction. So they are parallel, theta 0. So the small flux through the area element will be E ds cos 0, or the small flux is E into ds. simply E into ds. So the small flux through the area element is E ds. Now this is the small element d phi, but if I have to find the total flux over the Gaussian surface, then you have to integrate over the total surface. So surface integral, the surface integral of the total flux over the enclosed surface. So the total flux through the Gaussian surface, it is the surface integral of the individual flux through each element. So it is surface integral of E dot ds, but E dot ds we have evaluated as E into ds. But I have taken the Gaussian surface in such a manner that the shape of the Gaussian surface symmetrical to the shape of the charge that is being given, such that the electric field at all the points at the Gaussian surface is seen. So the magnitude of the electric field at all the points on the Gaussian surface is same. So this magnitude is same. So I can remove the constant. This is a constant. So I can remove the constant out of the integration of this thing. So the total flux through the Gaussian surface is E integral ds. Right? Since electric field intensity has same magnitude, E being a constant at all the points magnitude wise, so I have taken out of the integration. Right? So this is E dot ds. Now integral of the surface integral of the surface area, the total surface area, if I consider the area element here, over here, considering all the area elements, the total integration of all the things, now this is equal to, so the total flux is equal to E into, we know the total surface area of the sphere is 4 pi r square. R is the radius of the, small r square, where small r is the radius of the Gaussian surface. We have imagined the Gaussian surface to be at a distance small r. So it is area of the Gaussian surface we have to find out. So it is E is into 4 pi r square, the total flux, right? So therefore the total flux phi t is E into 4 pi r square. This is equation 1. Now next, applying Gauss law. So I was telling you, Gauss law states that the total flux from an enclosed Gaussian surface is 1 by epsilon naught times the total charge that is enclosed inside the Gaussian surface. So our Gaussian surface is a sphere. This is the Gaussian surface. The charge enclosed inside the Gaussian surface is Q. So therefore, according to Gauss law, the total flux from a Gaussian surface is the charge that is enclosed inside the Gaussian surface. The charge enclosed inside the Gaussian surface is capital Q. This is the charge inside the Gaussian surface, capital Q, by epsilon naught. So this is equation. So from equation 1, it is total flux to the surface is E into 4 pi r square by the definition of the flux. And this is from Gauss law. So equating 1 and 2, both equating 1 and 2, I get. So therefore the total flux E into 4 pi r square is equal to the charge Q by epsilon naught. Right? Q by epsilon naught. Now take this down there. So the electric field intensity at any point on the Gaussian surface, this is 1 by 4 pi r square Q by epsilon naught, or the electric field is 1 by 4 pi epsilon naught Q by r square. This is the magnitude of the electric field E. Electric field intensity due to a spherical shell, charged spherical shell, hollow sphere, charged hollow sphere. Electric field due to a charged hollow sphere or spherical shell at a point outside the sphere at a distance smaller is 1 by 4 pi epsilon naught Q by r square. This is the electric field magnitude. What is the direction? So the direction is along the outward normal. The radius vector, it is along the outward normal, but the radius vector of the radius vector from the point O, this also exists in the same direction. So this is r bar radius vector. So vectorially I can represent this as the electric field at any outside point of a spherical charged hollow sphere. Vectorially I can represent this as 4 pi epsilon naught, it's Q by r square times the direction of the electric field is along the radius vector. So the direction is given as r cap. You know, the unit vector along radius vector. Unit vector always represents the direction. So to imply any direction to a vector, then you have to multiply the unit vector along that direction. Magnitude into unit vector gives the vector. So the magnitude into the unit vector in the direction gives the electric field intensity vector, right? So therefore, E bar is equal to 1 by 4 pi epsilon naught q by r square. Well, r cap I can write as r bar by mod r. So E is equal to 1 by 4 pi epsilon naught q by r cube times r bar. So this is the vector form of the electric field intensity at any outside point of a charged hollow sphere, right? Thank you. Electric field intensity, the vector form of the electric field intensity due to a charged hollow sphere, charged spherical shell, E bar is 1 by 4 pi epsilon naught q by r cube into r bar, or 1 by 4 epsilon q by r square r cap direction. Magnitude is E 1 by 4 pi epsilon q by r square. Please look at the equation expression for this electric field. So the electric field here 1 by 4 pi q by r square, it is same as the electric field due to a point charge we have derived earlier. The electric field due to a point charge at a distance r from it, we have got the same formula, right? So for any outside point on the charged hollow sphere, the electric field is same as that on the that of a point charge at a distance r. So by comparing that and this, the electric field intensity due to hollow sphere and the electric field due to the point charge. Suppose if I imagine a point charge q at a distance r, here the electric field due to a point charge at a distance r, we have found the formula E same as 1 by 4 pi epsilon q by r square. So these two are same, the expressions are same. So by comparing the expressions, by similarly comparing the things there, the hollow charged hollow sphere will behave as a point charge, as if all the charge is concentrated at its center. So by comparing this expression, we understand that the expression for the point charge and the expression for the hollow sphere is same. In the sense, the charged hollow sphere behaves as a point charge, as if all the charge is concentrated at its center. So whenever you are given with a charged hollow sphere, charged hollow sphere, we can imagine all the charge to be concentrated at its center here, Q. Imagine as if it is. It doesn't really exist. It is imagined like that. So you can imagine all the charge to be concentrated at the center, and you can evaluate the expression for the electric field at the outside point. Right? So all the charge, it behaves as if all the charge is concentrated at the center. It is just a imagination, but really it does not exist. There are no lines of force inside. Actually, there is no charge inside the sphere. But with respect to the outside point, you can imagine this hollow charged sphere as if all the charge is concentrated in the center. Considering it as a point charge, you can evaluate the things. You can apply Coulomb's law, right? Wherever there are such calculations, such manipulations outside, then you can simply apply Coulomb's law by considering all the charge to be at the center. So this is a very important point. So a hollow charged sphere, when you are evaluating things with respect to any point outside the sphere, all the charge can be imagined to be existing at the center of the sphere. So this is equivalent to the charge that is at the center, and you can just evaluate the things. But mind you, this is only while evaluating the things outside the sphere. Right, when the point of concentration is outside the sphere, then the imagination, you can just imagine like this. This is actually called the Shallot Theorem. This is called Shallot Theorem. Right, according to this theorem, whenever you are evaluating any electrical parameters outside the charged hollow sphere, then we can imagine all the charge on the sphere can be imagined to be existing at the center. Right? So considering all the charge existing at the center point, you can imagine it as a point charge. So considering it as a point charge, you can evaluate the electrical parameters at that point Q. Right? So this is Shallot Theorem. According to this, Whenever a charged hollow charged sphere, when charged uniformly over the surface, then it can be imagined such that all the charge is concentrated at the center of the sphere, using which you can evaluate the electrical parameters at any point outside the sphere. Right? So this is the theorem there. So a hollow charge sphere behaves as a point charge where all the charge is concentrated at its center. Good. So this is the electric field at the outside point. Right? One more thing. Sometimes instead of giving you the charge on the charged sphere, he will be giving you the surface charge density of the charge sphere. A hollow charged sphere is uniformly charged on its surface, whose surface charge density is sigma. Now he will be giving you sigma instead of charge. Now when he gives you surface charge density, then how to evaluate this formula? Now you have to convert, you have to change the terms from surface charge density to charge then. So we are now given with surface charge density sigma, but we need charge to be substituted here, some charge. So we know surface charge density, I was explaining in continuous charge distribution, whenever charge is spread on a surface plane, the surface charge density, it is the charge per unit area. So surface charge density is Q by A. Let the charge on the sphere be capital Q. Now what is the surface area of a sphere? We know the surface area is 4 pi r square. So therefore sigma is equal to Q by 4 pi r square. So cross multiplying. When surface charge density is given, then you can take the charge on the sphere Q as cross multiplying. It is sigma into 4 pi r square. So this will be the charge on the sphere if surface charge density is given. Then putting this in these values in this formula, what we have derived. So the electric field intensity at any outside point of a outside point. So we have evaluated the electric field intensity at the outside point as 1 by 4 pi epsilon naught Q by r square, where Q is the charge on the sphere. Now here we are not given with charge, we are given with the surface charge density. When surface charge density is given, charge can be rewritten as sigma into 4 pi r square. So substituting here, this one, equating this, it's 1 by 4 pi epsilon naught. Q is sigma into 4 pi r square by small r square. 4 pi cancel. So therefore we get the electric field intensity. Electric field intensity at any outside point is E equal to sigma capital R square epsilon naught small r square. It is sigma times capital R square by epsilon naught into small r square. Right? So therefore, in terms of surface charge density sigma, it is sigma r square by epsilon naught r square. Here the formula electric field, it is proportional to 1 by r square. It obeys inverse square law. Here also electric field proportional to 1 by r square. Electric field depends upon the charge, the quantity of charge on the hollow sphere. Here the electric field depends on the surface charge density of the hollow sphere times the radius square. Right? So therefore electric field intensity at any outside point sigma r square by epsilon naught r square. If I write this in vector form, it is sigma r square by epsilon naught small r square. Now I have to associate the direction. I have to associate the direction also to this. So the magnitude into a vector is equal to its magnitude times the unit vector in that direction. So electric field direction is along the radius vector. So therefore it is r cap like this. Is it? So vectorially you can write the electric field as magnitude times the direction along the in the direction of the vector. So the electric field is along the radius vector. So therefore electric field vector is magnitude of the electric field times its unit vector. Or I can write this as sigma r square by epsilon naught small r square into r bar by mod r. So magnitude multiplying here, E bar is sigma r square by epsilon naught small r cube times the r bar vector. You see the expression for the electric field intensity at the outside point, right? It is sigma r square by epsilon r cube times r bar. right? If it is in terms of unit vector, sigma r square by epsilon r square into the unit vector along radius vector. So the expression for the electric field in different forms, in any form the question can be asked in the entrance examination. To confuse you, he will put it in different forms. The same thing, simple formula. First, simply, what is the electric field due to a hollow sphere at outside point? A hollow sphere, whenever you are comparing the electric field at the outside point, a hollow sphere behaves as a point charge, as if all the charge is concentrated at the center. So this is the first point you have to remember. So therefore, for a point charge, we know the formula 1 by 4 epsilon q by r square. So the simple formula is 1 by 4 epsilon q by r square. Now, if it is given in terms of vector, in vector, this is simple magnitude. If it is in vector form, then it is E bar is 1 by 4 epsilon q by r square. Now this is the magnitude. You add up the associated with the direction. Direction is r cap, because the electric field is along the unit vector of radius. Now, if it is in terms of r bar, now this is unit vector. No, if he has given the radius vector in terms of radius vector, then the same expression can be written as 1 by 4 epsilon q by r cube r bar. These are the values, these are the things when charge of the sphere is given. Now instead of charge, suppose if he gives you surface charge density, then the magnitude of the electric field intensity. This is the magnitude of electric field intensity E outside point, at any outside point. Surface charge density into capital R. Capital R is the radius of the sphere, radius of the charge of sphere, and small r is the distance of the point. So sigma r square by epsilon r square. Well, in terms of direction, vectorially, it is sigma r square by epsilon r square times r cap. And if it is in terms of r bar, sigma r square by epsilon r cube into r bar. Please make sure that for unit vector it is r square, when it is radius vector it is r cube. Right? You should be keen regarding these things. Thank you.